Let's go ahead and continue with the notes over here. We left off over here at this part 3, how atoms differ. Okay, so let's look at that section here in the notes. So it says here how atoms differ. So believe it or not, atoms are a little different. Not just the gold atoms are different from oxygen atoms. Yes, they're different. But I'm talking about oxygen atoms are different from other oxygen atoms. They're both oxygen, but they're just a little bit different. So let's go ahead and look at this part here. It says here, though, the atomic number. So let me zoom in just a little bit, and I'll have to move it over. It says, so who came up with this atomic number? That's what we're talking about right here. We consider him to be the father of the periodic table, Mendeleev. See, the father of the periodic table. Now, even though he's considered to be the father of the periodic table, believe it or not, his periodic table was revamped and changed up and reorganized multiple times afterwards. Now, they are arranged, the elements here, based on the atomic mass. Okay? Not atomic number. Okay? Not the atomic number is what he had. So it says here, look through the modern periodic table. What do you see? At least 2 elements that would have been arranged incorrectly in Mendeleev's table. Okay, even though he's considered to be the father of the periodic table, sure enough, he did have some mistakes, and one of them would be Ni, nickel, and iodine. Okay. So let's keep going. Now, Henry Moseley, back in 1912, discovered that atoms of 2 different elements contained, it says here, different numbers of protons. But the periodic table but the PT, and I think this is the first time we've seen it so far. That is the shortcut for periodic table. So the shortcut written is PT in order of atomic number. So again, it was trying to be rearranged. So let's go ahead and look at that atomic number. We kind of talked about it a little bit earlier up here and the previous page. Okay. So it says Henry Moseley. Let's look at the atomic number here regarding this. It says here is the number of protons, remember P with the positive sign behind it, and an element. So the atomic number is the proton number. How many protons does a gold atom have? Well, when you look at the periodic table, gold is number 79. So that's its atomic number. So that means he has 79 positive protons. How about an atom of aluminum? How many protons does that have? Again, going to the periodic table, looking at it, it would be number 13. What about how many electrons then an atom of gold? How much does it have? We're going to get that atomic number. We're going to subtract it from the atomic mass. And remember, from the atomic mass, we determine whether or not we're going to leave the number as is or raise it up by 1. Okay, we will round if needed and subtract those difference, and that would be the neutron number. But the electron number is going to be the same number as the number of protons. So it's 79. And an aluminum atom, again, to find the neutron number, you would get the atomic number and atomic mass, subtract them, right? Because the protons and neutrons is the atomic mass number, because that builds up the mass. But in this case, though, we're looking for electrons. How many electrons does aluminum have? It has 13 electrons. Now, why does it have 13 electrons? Why does gold have 79 electrons? Because atoms are considered to be electrically neutral. And for them to be neutral, they have to cancel each other out. Okay? So let's keep going on here. Let me turn my page and my notes. And we're going to talk about this word over here, isotopes. Okay. And before we get to isotopes, we are going to fill in these two blocks over here. Henry Moseley discovered that atoms of two different elements contains different number of protons. Two different elements. So they're different elements and they're going to have the different number of proton. So that means that they're going to be put in order to their atomic number by the number of protons they have. And so that's what Henry Moseley came up and decided. So the periodic table literally starts with the number 1, hydrogen. Starts off with the number 2, helium. And it goes in order just like that. Okay, that's what the top part right here was saying. Sorry. Now we can go forward. Moving forward, though, they move on to this other word called isotopes. Okay, now isotopes, what's important about that word here is that it's an atom of the same element, but it actually have different number of neutrons. Okay, so isotopes were discovered and they are the same element, but they actually have different number of neutrons. What makes them the same element? Because they have the same number of protons. Okay, neutron number is different. Okay, now this, when the discovery of isotopes came around, it disproved Dalton's theory. Dalton said that all atoms are the same element, they were all alike. Okay, all atoms of the same element must have the same number of protons. I agree, that's a true statement, but not necessarily the same number of neutrons. He didn't know about that at the time. Okay, says here, example, potassium. There are 3 different kinds of potassium atom out there. Okay, so for an example, potassium 39, potassium 40, and potassium 41. Now, that means let's go ahead and look at the periodic table. Hopefully you've printed one out and you have one with you. Let me go ahead and get my periodic table. I have an older one over here. So potassium 39. Well, let's go ahead and let's look at potassium. Potassium is over here. It's a it's a metal. Potassium is K. It has the atomic number of 19, and here's the atomic mass of 39.098. And we are going to leave it at 39. Do not round it up to 40. Okay, so I'm going to come over here and I'm just going to write just for myself so we can fill in this chart. The atomic number is 19. The mass number is 39. We round it to a solid whole number. Alrighty. But if you ever wondered why they all have decimals for their mass, this is the reason why. So let's look at this box over here. For potassium number 39, when I go to the periodic table, I know that the atomic number is 19. For any atom to be that atom, its atomic number determines it, if that makes sense. Kind of like once you get a little older and you get a driver's license, you will have that driver's license number forever. And that driver's license number is always going to be you and you only. Or you have a social security number. That social security number, every time they look it up or they type it in the system, it always comes up as you. It's always going to be you. You have something, your DNA, it's always going to be you. So for here, for potassium, for it to be potassium, it has to have an atomic number of 19, which means that whether it's potassium 39, 40, or 41, it's going to have 19 protons no matter what. So again, when they look up your driver's license number, your social security number, it's going to come up as you, no matter what. Now, let's come over here and we know what the mass number is. We have over here atomic potassium 39, potassium 40 and potassium 41. When you get those numbers like this, this is the mass number for this. So those numbers are actually the mass number. This number that's on the periodic table is the average mass number. So they get all of those masses, they average them out, and that's what they come up with. And that's what they put on the periodic table. Okay? So if you're going to average a number out, more than likely you're not going to end up with a nice pretty whole number. You normally end up with some kind of decimal, like over here. Where do they get the decimal? It's because they're averaging out all the different types of potassium. So in this case now, I'm going to go ahead and get 39, take away 19, and I got 20 neutrons. I'm going to get 40 and take away 19, because that's the atomic number, that's the number of protons. 40, take away 19, I've got 21 neutrons for here. And this one is 41, take away 19, and I've got 22 neutrons here. Now, where does the atom's mass come from? It comes from the neutron number and the proton number. And so this one and this one, they have more neutrons, so they are going to weigh more. They're going to have more weight on them, okay? Kind of like, now let's pretend you get your driver's license number and they look your driver's license number up, and 25 years from now, there's a good chance that whatever you weigh right now as a teenager is not going to be the same weight as when you are 25 years older from now. Okay? You're still the same person. They're still the same person. They're still going to be potassium. It's just that they have aged and they've gained some weight, if that makes sense. That's how I think of it. They have gained some weight. Now, what is the electron number? One more time. I'm going to go ahead and write it over here. All atoms are considered to be electrically neutral. So if they're all going to be electrically neutral, then that means that if you've got 19 positive protons, you have to have 19 negative electrons. 19 positive protons, 19 negative electrons. 19 positive protons, 19 negative electrons. Now, does it stay that way? Truthfully, no. They gain and lose electrons. And when they gain and lose electrons, we call them ions. And we're going to talk about those as well. Okay? They become what we call ions. Okay? So they don't stay this way, 19 and 19, 19 and 19. They don't stay this way. They actually change because they have to gain or lose electrons to become happy in their outer shell. And when that happens, they become what we call ions, okay? So it says here, there are actually two ways for the symbol, to write a symbol with the isotope. This is one way, potassium number 39. This is another way, potassium 40, potassium 41. Now, this number right here is the percentage. So for an example, if I was to get a big chunk of potassium, and I was going to sort through every single atom of potassium, 93.25% of the time, it's going to be potassium 39 inside there. So if I had a big bowl or a pie of potassium, and I looked at every single atom in that big pie, 93.25% of the pie, which is almost all of it, is going to be potassium 39. 6.73% of it is going to be potassium 40, and 0.12% is potassium 41. Okay? Now, those isotopes, there's two ways to write that isotope. Either number one, they can write it like this, kind of like how we saw it up here, or number two, they'll write it like this, where this is the mass number, the 39, the 40, the 41, and this is the atomic number down here, right? The 19, 19, 19. Alrighty? So let's keep going. Let's talk about mass number. So now that we've already discussed a little bit about that, isotopes, mass number, we said earlier, but we're going to say it again, contains the proton mass and the neutron inside there. Okay, the number of protons plus the number of neutrons. The atomic number identifies the element of who he is. The mass number identifies the isotope. Okay? Isotope similarities. Now let's talk about that. It says here, chemically and physically, they're alike. So whether or not it's potassium 39, 40, or 41, chemically and physically, they are going to look exactly alike. Okay? So I guess we can say you now this year, and you next year, and you the year after that. 3 years, that's 3 different yous. It's still a you, but it's going to be you at 3 different years. You're probably still going to be the same. You're probably going to still kind of act the same. You're probably still going to do things roughly the same because that's who you are. Okay? So when it comes to isotopes, they chemically and physically are pretty much alike. The only difference between them is going to be that number of neutrons. Now, the reason why chemically that they're going to be alike is because the number of electrons determines the chemical behavior. How reactive, how is it going to chemically react with another substance is all determined by the electrons. They do the chemical bonding, okay? Not the proton and the neutron number, no. So it says here, same number of protons and the same number of electrons. That's why they're chemically and physically the same, okay? What is different between them? The number of neutrons, which causes it to be the mass number of them are different, okay? Let's keep going in our notes. Isotopes. Let's talk about and look at the differences between isotopes now. So, a couple of differences. Number one, we've already said the number of neutrons. That's different between those isotopes. Even though they're the same, they still have different number of neutron, which makes the different mass numbers, the different masses of them. And they're going to have, because they have different masses, then they have different mass number. Alrighty, so let's go ahead and look at a chart like this. Be familiar to go ahead and do this on homeworks. This will be on a quiz. This will be on a test. Okay, it may not have this many blanks in it, but be prepared, even if it's just one column on one row like this, to fill in the rest. So if they're giving you one number, you need to fill in the rest of the numbers in this row. And then the next row, they give you one number over here, you need to fill in everything. This one, they gave you 2 numbers, but you need to fill in all the other blanks. So let's look at the first one, neon. And this is where you're going to need to have printed out your periodic table. Neon's over here in group 18. Here he is. Look at his atomic number, number 10. So let's look. His atomic number is 10. His mass number, they told us it's 22. Let's look at neon. This mass number says 20. So what does this mean over here with this mass number? That this neon is a little different. He has more mass. The number of protons. What determines the proton number? The atomic number. So it has to be 10. Also, though, we know that atom's supposed to be electrically neutral. So if it has 10 protons, it has to have 10 electrons. Pretty easy. We're going to fill in this chart. It's going to be really easy. The number of neutrons. How do I find the number of neutrons? I get the mass number and I subtract the atomic number. So 22 take away 10 equals 12. Now let's go ahead and write the symbol over here. Ne is who he is from the periodic table, neon. And we absolutely know that he is definitely going to be a isotope, but either way, we're going to write it this way. He has the, remember what it says, mass number goes at the top and atomic number at the bottom. There we go. Not bad. Let's keep going. Calcium. Okay. So when we look at calcium over here, calcium is a metal. It needs to be a metal. Calcium, right, determines your bones, makes up your bones. It better be pretty strong. So calcium's over here with the other metals. It has an atomic number of 20. So atomic number of 20. If it has an atomic number of 20, then its proton number better be 20. If its proton number is 20, then its electron number better be 20. Okay? So I'm going to come over here. What was his symbol? Ca. The first letter is always capital, C and the A. And remember, when we write it this way, then the atomic number, which is 20, goes at the bottom. Now let's keep going and filling in. Did I leave something? I did. Mass number. So when I come over here to mass, let me look. Now the chart here says calcium has a mass of 40.078, so we're going to leave it at 40. Okay? What determines the mass of an atom? The protons plus the neutrons, those two together equals the mass number. Okay? Now they told us that the neutron number is 26 over here. So in this case then, 20 plus 26 would equal 46. That's not what the periodic table says, Miss Munson. Well, then this must be what kind of an atom? An isotope of calcium. Okay? It's still calcium, but it's an isotope form, which means it has more neutrons, which means it has a bigger, heavier mass. So over here now, we're going to always put the mass number, which is 46. We found that out. Let's go to the next one. Oh, they didn't give us the name, but they did say the atomic number is 8. And no matter how much weight it gains, it's still going to have the same number. Just like no matter how much weight you may gain in the future, you're still going to have the same driver's license number, which always goes back to who you are. It's always going to come up when they type in a driver's license number that it's yours because you get one day, your name is going to pop up. So let's go ahead and look at this. Pretend it, right? It's a driver's license number. It's number 8. Who's number 8? Oxygen will always be number 8. No matter how much he weighs, he's number 8. So this is oxygen. His symbol is just an O by itself. Okay? So let's go ahead and get started. If his atomic number is 8, then his proton number must be 8, and his electron number must be 8. The neutron number. Well, how do I find out the number of neutrons? I'm going to come over here, and I'm going to get that mass number of 17 and subtract the atomic number of 8. And I'm going to find out that there's 9 neutrons left over. Okay? So over here, atomic number of oxygen is 8. The atomic mass of oxygen, it has over here of 17. Let's keep going. The next one. They gave us these two numbers. And the first thing I know is that if it has whatever proton number, it has the same electron number, 26. And if that's the proton number, that is its atomic number of 26 also. So let's use the periodic table. Let's go look up 26, and 26 says iron. Iron. And the symbol is a capital I. And at the bottom, the atomic number, which is going to be 26. Now let's keep going. We need to fill in the mass number. What is the mass number? The mass number is always going to be the number of protons and the number of neutrons. And it may not be the same as this periodic table. Why? Because they may be talking about an isotope. I don't know. But what we're going to do is we're going to add this number plus this number. And when we get those together, it's going to equal the mass number. So 30, 40, 56, 57. So 57 is the number over here, which is going to go over here as well. 57. Let's look. 57 iron. 55.8. Normally we would round it up to 56. So obviously this as well is an isotope. Let's keep going. This one, they gave us over here zinc of 64. What is this top number over here? This top number is the mass number. So let's write that in. 64. Zn. Let's come over here and let's look. Zinc. Zn. Here he is. His atomic number is 30. So let's write that in. And remember, atomic number 30, proton number is 30, electron number is 30. Okay, zinc, Zn is his symbol. And let's go ahead and spell out his name, zinc. Now, we know that the neutron number, if we need to figure that out, we would get the mass number of 64 and subtract 30, and we would find out what is left over, 34 neutrons. And what goes at the bottom over here is going to be the atomic number 30. Alrighty, let's keep going. Last one. They gave us neutron number and electron number. Now I know the neutron number could change. Why could it change? Because it could be an isotope. Alright? But one number that will always stay the same because they are electrically neutral would be the electron number. And if I have 80 negative electrons, I better have 80 positive protons. And if I have 80 positive protons, then my atomic number is also 80. So let's go look up and see who 80 is. 80, mercury, Hg. Okay, so I'm going to come over here, I'm going to write Hg, and I'm going to write 80. All right, so let's go ahead and let's fill this in. M-E-R-C-U-R-Y, mercury. Now, what is the mass number? Remember, we've done this quite a few times. The proton number plus the neutron number equals the mass number. So in this case, 80 plus 124, double check me, I think that is 204. Okay, so we filled in the chart. Yes, we need to be prepared to fill in the chart for quiz day. We need to be prepared to fill in this chart for test day, as well as it's on homework. It's throughout many homeworks, so you will have a lot of practice with this chart. Next part is atomic mass. All right, so they want to talk a little bit more about atomic masses. All right, we can do that. So it says here that atomic mass is the weighted average mass of the isotopes of the element. Okay? And I just mentioned that. This one here has decimals. Why do they have decimals for their masses? Because that's the average of all the different masses of the isotopes. So the atomic mass number, if you ever wonder why they have decimals, it's because it's an average of the mass of the isotopes. Okay? So we have a number up here, which looks like my periodic table, little blocks, right? That is the atomic number. And this number down here is the mass number. And that mass number is the average of the isotopes for chlorine. Okay? So let's go ahead and let's look at this. It says AMU. That is definitely going to be either a quiz or test question. So I would be prepared for like maybe some kind of matching or something. Or even it might just be a multiple choice, A, B, C, D. But AMU stands for Atomic Mass Unit. Atomic Mass Unit. And it says here, 1 AMU is equal to 1/12 of the mass of a carbon-12 atom. Now, when we looked at all the isotopes and weighing them, we compared everything to carbon-12, okay? Because it's just so abundant. So it says here, proton equals 1 AMU, a neutron equals 1 AMU. And what do we say about the mass? Because we're talking about mass. What do we say about the mass of electrons? They're almost weightless. Like, they're just so insignificant. 0 AMUs. So the electrons has no meaning, no matter, no number within the AMUs, within the atomic mass unit. We don't take those electrons into account. Usually not a whole number, right? Remember we talked about that. Those numbers here are pretty much not whole numbers. They're pretty much going to be decimal points, right? Why? Because of the average of the isotopes. Now here's an equation. Let's look at this equation. You can actually figure out the average atomic mass. So the equation here, which is on your formula chart, of the average atomic mass equals the percent abundance times the mass number plus the percent abundant times, oops, I shouldn't have stuck that, parentheses, times the mass number and I put dot, dot, dot. Why did I do that? Because this is the first one, this is the second one, and it may have 5 different isotopes of that element. That element may only have 3 isotopes that exist. That element might have 6. So you have to do that for all of them, and you add them all together, and that's what the average atomic mass is. Okay? So, but we do that for all the different isotopes. So I'm going to put right here. This right here is isotope number 1. And this one is for isotope number 2. And so on and so on. Okay? Let's keep going. We've got a couple of practice problems on this. It says here, calculate the average atomic mass for chlorine if it actually contains 2 naturally occurring isotopes, chlorine 35 and chlorine number 37. What is the number at the top? That's the mass number, not the atomic number. Now, chlorine 35, when we look at it in the world, if we were just to grab different, like a big chunk of chlorine, 75.77% of it would be chlorine 35. Okay? 24.23% of it would be chlorine number 37. So let's go ahead and let's practice this. There's only 2, so we're going to have to do this twice. Let's do the first isotope and the second isotope. Add them together. When we do this percent abundance, we need to, let me go ahead and put a little note here. We need to, with the percent abundance, change into decimal. Take it out of a percentage and put it into a decimal. Okay? So now let's go ahead and practice. Well, how do we take it out of a percent? Well, we move the decimal place over to the left 2 times. 1, 2. So 0.7577 times 35, which is the mass of isotope number 1, plus